This is chapter 12, tests of goodness of fit and independence. So we start with a goodness of fit test for a multinomial population. What is a multinomial population? It is an extension of the binary population we discussed in the previous chapters. In binary population, we have only two possible values in the population, success or failure, 0 or 1. Or another example would be like smoking or non-smoking. But if you extend that, instead of only two possible values, if you have more than two possible values in the population, then what we have is a multinomial population. So examples like for grades of students, okay, in a class, you can have either A, B, C, D, or F. It's more than just two, several possibilities. Another example is if you conduct an opinion survey about some issue, you either favor or oppose, or maybe one possible answer is don't know. Or membership in political party, okay, the Democrat or Republican or independent. So if you have a population that has more than just two possible values, then what we have is called a multinomial population. So when you have a multinomial population, we can test for a predetermined probability distribution for the value. So like if you have A, B, C, D, and F, and you assign probabilities, 20% A, 20% B, 40% C, and so on, and you want to test whether that assumption is true or not. And so you can conduct a goodness of fit test by taking a sample and testing this hypothesis. The hypothesis that we want to test is whether the assumed probabilities, so you assign a probability for each possibility, and that is true or not. And notice here that if you sum all these probabilities, it should equal 1. So you take a random sample, okay, size n, and there are k categories. That is, if you have A, B, C, D, and F, and there are 5 categories. In the second example, there are 3 categories, and so on. So number of categories. Now in each category, how many of the sample observations fall? And that's F sub I, observed frequency for each category in the sample. Of course, when you sum all these observed frequencies, and that should equal the sample size. Then these F sub i's are the observed frequencies in the sample. But if the hypothesis is true, if these are the probabilities for each category, then we can compute what is called expected frequency by multiplying the sample size with the given probabilities. So if the probabilities are true, then these are the expected frequencies that you will see in each category. Then we can arrange these in a table form in this fashion. So you have the population values, there are k categories, and these are the probabilities that we have assumed in the hypothesis. These are the sample frequencies, and then when you multiply sample size n times each of the probabilities, you get the expected frequencies. So we have the observed frequencies and the expected frequencies, and if the observed frequencies and the expected frequencies are very close to each other, then probably the null hypothesis is true. Maybe the probabilities are valid. But if the expected frequencies and the observed frequencies are different, significantly different, then maybe the probabilities are not as stated in the null hypothesis. So we can calculate a test statistics called chi-squared calc by finding the difference between the observed frequency and the expected frequency, square it, and then you divide by the expected frequency for each category, and then sum all of them, and you get a chi-squared calculated statistic, which can then be used to determine the p-value. But first, we need to make sure that all the expected frequencies are greater than or equal to 5 for the test to be valid. If this is not so, then one way to mitigate that is to increase the sample size. You take a larger sample, then you will have all the expected frequencies greater than or equal to 5. Or we can try to combine some of the values so the expected frequencies will all be greater than 5. Then the test statistic is what we calculated. We can use that test statistic in the Excel function chi_sq.dis.rt, and here the degrees of freedom is k minus 1, and that will give us the p-value, and based on the p-value we can make a conclusion. So in the next video we will look at a numerical example.